Continuing on with class number 4, and here's example 2.4. We have a rigid vessel that contains saturated ammonia vapor at 20 degrees Celsius, and heat is transferred to the system until the temperature reaches 40 degrees Celsius, right? One thing that we know about this is that the specific volume has to remain the same in a rigid vessel because the mass remains the same and it's rigid, so the volume remains the same. That's a good thing to recognize right here. I'm trying to take, oh yeah, okay, so below is the diagrams of these already given, they're giving it away, where they said the red circle indicates the two states in which they are taking interpolation. We'll see that in a second in the, so we'll come back to this and take a look at the thing. But first we're going to start out with that 20 degrees Celsius, and that it's, so there's seems to me that we would need to know a little bit more about this. Oh, it's saturated. That's right. Saturated ammonia vapor. That was the reading comprehension portion of the thing. So let's take a look at our book. And let's take a look at this problem. This is more practice. So we have ammonia. And so what we will do is we will take 20 degrees. So we have 20 degrees. Where'd you go? 20 degrees. And it's a saturated vapor, right? So we're going to write that down, 0.14922. So at table 8.2.1 at T is equal to 20 degrees. VG is equal, and we might want to find out right here. It's also good to know what the PSAT is. We can, one of the questions you could ask was, what is the change in pressure? And that's the 20 degrees. I'm looking at the table here. It's 728.6 kPa. All right, so we have VG, and VG is going to be like 1492. That's a good way to remember it. 1492 cubic meters per kilogram. I've been getting those reversed lately a lot. And so this thing is going to be constant. So we want to go to table 8.2.2, and at T equals 40 degrees Celsius, we're going to have to look for what pressure. Okay, we're going to have to look for the pressure where it has this combination of 40 degrees Celsius and this specific volume, right? So that's not necessarily an easy thing to think of. So let's check it out right here. Okay, so first off, let's just go to the very first one and take a look. All right, so that's 3. That's way higher than we need. We want like 0.14 right there. We're going down with increased pressure. Okay, let's check it out down below. 40. All right, so here's less. Okay, there. Ooh, okay, at least we're below 1, but we're still way too high. Let's go over to the next page where we are looking for, okay, and we're still at 40 degrees, 0.3 is at the 400 kPa. Ooh, wait, this is looking promising. 0.29 and 0.24, still too high. We want 0.14. I just jumped to this one, 40. Ooh, wait. That's pretty good, right? In between those two, are we in between? So what we've just discovered is that we are in between 800 and 1000 kPa. So now we want to do an interpolation in between there. We already know it's 40 degrees, and we know that it is a value between these two, so we can find out what that pressure is. So we need to write out an interpolation table, or let's make the left-hand side the thing we know. All right, so here's what we're trying to get, 1.14922. That's the thing we're trying to get. Let's see, the one that's over here in the 800 is 17720, right? So we'll go 800 and go 0.17, whoop, I forgot the one. 17, where'd you go? 720. And then down over here, this is the 1000, yes, the 1000. And for 1000, we're going to get, for right here, 0.13868. 0.13868. And then this is the pressure that we want to try to find. And as I said, I like to just go like that right there. Makes it easier, just a nice little routine. 0.17720 minus 0.14922 divided by 0.1, whoop, it should be 177, right? That one minus that one, and then this one minus that one. So 17720 minus 0.13868 equals, and then we go 800 minus P. I like to put these parentheses around stuff. I don't know when I started doing it, but always made it look better to me. And then we're going to go 800 minus 1000. Notice that this is minus right there. It's going to be a negative 200. Check this out, and this ends up being 0.2736, right? So 27% of this range, which is going to be a minus 200. And we end up finding a P that's going to be 945.3 kPa. And you can kind of check that it's like, yeah, it's going to be a little bit closer to this one than it is to that one. I think I got that correct. I looked at that. I think I looked up the answer, and I think that's correct. But there you go. There's the interpolation. It's a little bit of a process. This has a part E to it. So let's go ahead, because the video is only 7 minutes long. We can follow through and look up the English units one, where we have 70 degrees Fahrenheit, and it's going to 120 degrees Fahrenheit, just to get some more practice in there. And did we say this was ammonia, or, yeah, it was ammonia. So just double checking that it is superheated at, first we wanted to get a value. We need a value. Okay, yeah, sure. So at 70 degrees, the vapor is 628. Is that true? It doesn't seem right. Am I doing something wrong? Oh, that's enthalpy. Oh, I see. Okay, I started on the wrong page. Right. There you go. All right, so these weren't facing page, like they didn't have on the same page. They were back to back instead of facing each other. So 70, and we end up with 2.3098. Great. So 70, and by the way, that has a saturation pressure of 128.85, but we don't really need to know it. But it's good to write it down, though, I think. Pretty good to write it down. So this is table, what is that table? F, I'll go right here, F.8. Once again, I'm looking at the wrong side. 0.1, great, thanks. And at T equals 70 degrees Fahrenheit. The only one I really care about is that VG, and we found out that is going to be 2.3098, and those are cubic feet per pound mass. All right, so that's at the saturated vapor, and then we heat that sucker until it goes to 120 degrees Fahrenheit. And of course, it doesn't have any choice but to have the same specific volume, because the volume doesn't change because it's rigid, and the mass doesn't change because mass don't change. All right, so we can start looking for this V. These numbers are way too large. We're looking for a number that's like 2.3. So we're jumping around here. By the way, look at it. They got rid of internal energy. They didn't care about that. We don't really use internal energy all that much. At least I don't. Nothing on this page is even close. Okay, yeah, we're going to start getting there. So what did I say? We need to have 2.3. Here's stuff in the ones. Here's stuff in the ones and the ones. Where'd you go, 2.3? Maybe it was on the previous page. Not seen it. Where'd he go? Oh, wait, down over here. 2.3. Maybe I didn't look on the right page. Oh, maybe I jumped a page. I think I skipped a page. Must have been it. Must have been it. Here you go. Here's some in the range right in there. That looks pretty cool. Don't think anybody else right there. So 2.3. No, what did we say? 120 degrees. Yeah. So right there, and it's got to be less than that. It's going to be 120 degrees, 2.7. Yeah. So right here, 2.7 at 125, and 2.2275 at 150. All right. So that's the thing we want to try to do. So it's going to be somewhere between 125 and 150. So setting up our interpolation table, we have to decide which way we want to go. I'm going to go 125 up at the top and 150 down below. And so that's going to be the pressure. And so the values that we're up on there at 120 degrees looks like it's 2.7177 and 2.2275. And so we're going to stick this 2.3098 into there and interpolate. That right there, or there, and that one right there. And so we go 2.7177 minus 2.3098 divided by 2.7177 minus 2.2275. It's going to be equal to 125 minus P, it's the unknown, and 125 minus 150. And as I didn't do it this time. Let me put it down here then. 2.7177, 2.3098. You get enough of sig figs in there? Okay. And then 2.7177 and 2.2275 minus divided. And so this is like 0.83211 is the percentage that goes in there. But anyway, if you get the pressure from this, it's going to be 145.8. And this is PSIA. And another example. Gotta get good at this interpolation stuff.